Okay, we're in week 9. I just want to go just through this in the table of contents. We're going to be covering the exponential functions and graph in this lecture. Certainly, when we do that, we're hoping that, again, you listen to what we're presenting to you, try to digest what's presented to you, and try to understand, I'm not going to say completely, but partially. Of course, we'll go through examples. There will be supplemental activities that you need to practice with before you go to WebAssign. All right. What else are we going to do in this section 9? The exponentials are related to logarithmic functions, and we'll talk about log functions as well. Right. But the foundation is, do you have exponentials down? Did you practice the problems? Then you start moving forward. Then you go logarithmic functions. We'll talk about that. And again, I'll be in the next lecture. But the bottom line is step by step by step, but it requires work to take those steps. All right, so let me go to week 9. I'll just give you an overview of what we're doing initially. We're going to talk about what an exponential function is. We're going to talk about their graphs. We're going to talk about the property of exponents. This is something actually covered in Math 092 and Math 100, but we'll simply review that with you. Hopefully that stuff is understood. However, some students remain confused about what they learned in Math 100, and it can't hurt to go back and review that. All right, we'll talk, we'll give you good images. When I say good image that machines draw. I'm not saying people can't draw good images, just machines are much better at it. All right. So we're going to talk about a new number that you haven't seen before. That's called Euler's number. We'll talk about that number. And the other thing we're going to talk about is some formulas that you need to know about. And the formulas that you need to know about is a discrete compound interest and a continuous compound interest. There will be some application problems, typically in exponential growth and decay. We will certainly go through examples, but first lecture. I'm going to go to the whiteboard. Give it a moment to warm up. All right, I'm at the whiteboard. So let me go back to the page I want to go back to. And again, you should realize that lectures are relatively short. I mean, most lectures are relatively short. Some really do drone on for a while. But the bottom line is, let's just talk through the definition now. All right. So it's important that you read this. I'm not saying memorize it, but have some understanding what's being said. So what are we on now? We're on the exponentials. All right. Now, what are we talking about? We're talking about functions. So f of x is a function of x. And what is it? It equals a raised to the power x. With the understanding that x can be any real number, but the a must be positive. Another condition that we want is we don't want a to be 1, not because it's bad, but because it's really uninteresting. All right. So what do we know? We know the exponential function. I'll write this down for you. And we know the function f of x is going to be some positive number a raised to any real number. Now, when I say some positive real number, we're trying to exclude 1. Now, why is that? Let me repeat this again. The reason for it, it's not really interesting because 1 to the x is always going to be equal to 1. It's an uninteresting problem. All right, let me erase that. And again, we're not trying to confuse you. We're trying to get you to read the definition of what an exponential function is. All right, so the next thing up is going to be the graphs of it. And, I want to point out that, if a is a positive real number, we have a variety of possible graphs to construct. And now what do I mean by that? If a is a positive number, how many positive numbers are there? There's a tremendous number of those. Some are going to be proper fractions. Some of those are going to be bigger than proper fractions, right? Or improper fractions or whole numbers, all right? Like working whole numbers. Well, let's exclude 1 again, like 2, 3, 4. We try to keep it real simple though, all right? So I'm going to just say, in essence, what do we have? We have a variety of a's over here. So a variety. Now, a variety of what? A variety of a's. So this is the key part. There's going to be a variety of a's. So a, again, is going to be a large number of a's to choose from, all right? So again, all we know about a is going to be a real number, all right? We don't want it to be 1. So I'm going to say, it would be nice if you had some understanding when a is between 0 and 1, and some understanding when a is greater than 1, all right? Some understanding of those. Again, I'm not saying a memorization, an understanding of it, right? That's all we're looking for, all right? So what I want to do is I want to go to the next page, and my claim over here is to get an understanding of something, it's probably going to take a little bit of legwork, and that is walking through plotting points. Let me just go to the next page, and we'll talk about the graphs, all right? Put this over here, And I just want to go through this with you. And I'm going to talk about the red one first. And the red graph is y equals 2 to the x. Now, with the understanding that, 2 is the base of the problem, that's the a, it's certainly a positive number. It's greater than 0. And what I would recommend you do over here is just plot a few points to get a feel for this. What's the easiest point to plot? Probably 0. And if you plot 0, what do you get? Well, you get 2 to the 0, and 2 to the 0 is going to be 1. I'll plot that point. Let me plot another point. I would say 1's an easy number. Now, if you plot 1, what do you get? Well, 2 to the 1 is 2. So what do I get over there? I get this point right here. All right. Now, if I took the number 2, what would I get? I would get 4. So again, what upon we're doing, you're moving over 2, and then you're moving up, and you're going to hit the curve at 4. All right. I think you get an idea that if you're looking at those 3 points, I hope you notice a connection between them. The problem for a lot of students is they say, when do I stop? You stop when you know how it continues. For example, let's say I didn't know what happens next. I would pick 3. What's 2 cubed? It's 8. So 3 would give me 8, and I'll plot that point down for you. I'll connect that up. Now, if you want to the next thing, say, I don't know what's going to happen there, but what would you get? It's going to be a doubling, and you get 16. I hope you realize that as we move to the right, this thing is going up, and it's going up rapidly. All right, now let's move in the other direction, which is more difficult. We're going to move towards the negative numbers for x. For example, if you chose -1, what would you get? 1/2. All right, I'll put that down for you. -1 would give you 1/2. And I'm on the red curve, by the way. All right. Now, someone says, that's really tough for me to do, but you can do it. All right, you could actually do that. All right, so I'm going to put another number like -2. What would you give there? Well, 2 to the -2 is going to be 1/4. Whoops. Yeah, I made a mistake. Let me just back up. So if I want that, I'd be at 1/4. By the way, I have a feel for this as well, connecting it up. Again, if you want, you can keep connecting them. What I'm saying over here is that I think you should have an idea. The more negative I go, the smaller it goes. So I'm going to say it's asymptotic. All right, let me write this down for you. So, y to the 2x has an asymptote. And what is the asymptote? It's a horizontal asymptote. And what is a horizontal asymptote? It's the x-axis. It's always going to be positive. So 2 to the x is always going to be positive. Always. All right. What's a horizontal asymptote? It's going to be y equals 0. All right. Again, someone says, could you keep doing this for all the numbers in the universe? No, we just want to get a feel for it. And I want to do the green one now. So the green one is going to be, well, I'm looking at it. The green one is 20 to the x. Now that's a positive number, 20. It's being raised to a power. What would I recommend? A table of values. I would say 0 would be the easiest one to choose because 20 to 0 is just 1. I'll put the little green point down there for you. Now, if I took 1, it would be 20 to the first power, which would be 20. And this gets difficult. And I'll tell you why. I can't really graph it. And I'll tell you why I can't graph it. 1 is here. Where would 20 be? Well, this is 9. 20 is way up there, right? So I'm going to say I have a feel for it, that it's going up very, very rapidly, much more rapidly than that the red graph. So I'm going to say it goes up much more rapidly. And I'm hoping you get a feel for that. All right, and put that in for you. Someone says, yo, you didn't plot a point. No, but I know this thing's going up. And when it hits the number 1, it's going to be on the y-axis, it'll be 20. Now, if I did, the next one, if I did 2, which I'd hate to go there, what are you going to get? 20 squared. So let me just repeat that. At the number 2, this thing is really far up there. That's 400. I can't count there, but I know it goes up rapidly. All right, let's do -1 now. What would that give you? 1/20. Now, I hope you realize 1/20 is an incredibly small number. All right. If I did -2, what would I get? 1/4. Whoops, I did it again. You would get 1/400. All right. What does that mean? It's really small. All right. I'm getting a feel for this. Again, I'm just, when I get that, really not a very good drawer. So what do I know about it? And I'll write this down for you, and it's really not bad. Put this in white for you. If I have y equals 20 to the x, what do I know? Well, I know it is a horizontal asymptote again. And what else do I know? I know 20 to the x is always going to be positive. What's horizontal asymptote? Y equals 0. Does it go there faster than the other one, 2 to the x? Of course it does, right? But it still is asymptotic with that line, y equals 0. Let's do one last one. And again, you can play around with these if you like, and we'll do other examples when we take, when we go to the examples. But right now, I'm going to do the blue one. And what's the blue one? It's y equals 5 to the x. So I'll put x down and a y down. And what's the easiest one to put down? 0. What would 0 give you? Well, 5 to the 0 is 1. Well, that seems like a commonality between all these exponentials. Let me go to 1. What would that give me? 5. So if you're at 1, what do you get? You're at 5. That was easy to do. If you go to 2, what do you get? 25. Well, I hope you realize as I go in this direction over here, it is going up. And when you get to number 2, it's off the page. It's at 25. So it goes up pretty rapidly. Now, which one goes up quickest? Well, the one that goes up quickest is y equals 20 to the x. Which one goes up the slowest? Y equals 2 to the x. All right. The one in the middle, the blue one, sort of in between. All right. Let's take another number like -1. What would this give you? 1/5. And if I put -2 down, what do you get? 1/25. Again, they may be hard to plot, but they're really not that bad. What do I know about it? Again, it's asymptotic. All right. Let's write that down for you. Over here, what do I have over here? And we're just taking simple numbers. We have y equals 5 to the x. What do I know? There's a horizontal, that's 5. I know there's a horizontal asymptote. You know what, let me get my eraser out because it really doesn't look like a 5. There's a horizontal asymptote. What is it? It's the same. It's y equals 0. All right. What do I know? I know 5 to the x is a positive number. All right. I know that. All right. Pretty easy to do. All right. So we did this. We did this. And we did this. There's certainly commonality about these curves over here, that at 0, all the curves equal 1. Every single curve, they all share that. Which one grows the fastest? This one. Which one grows? When I say grows, I'm talking about moving left to right, increasing. This one increases the slowest. This is sort of in the middle. So I guess if you put an ordering down over here, you could do that with any given number. So for example, I put down y equals 50 to the x. I hope you realize that would grow faster than y equals 20 to x, so forth and so on. All right. Now, Graham, we haven't done fractions yet, but when we start doing problems, we'll talk about fractions as well. All right. So here's the deal. We just plotted some points over here. Let me go back to the prior page. And we're going to talk about things, a review of what you did in Math 100. All right. This is just a review of what you did in Math 100. So in Math 100, you have what called exponent rules. All right. They were extensively covered in Math 100, and you had a ton of problems with it. Do students, get through Math 100 having a full appreciation for this? Yeah. And I think really the main reason for that is there's really not enough practice in that area. So let's talk about exponents now. And what they say is that we have exponents now, and the exponents will be m, n, and p, and they're going to be real numbered exponents. All right. So what do they talk about? Rules. Now I'm going to just talk about it briefly. All right. And someone says, what does this mean to me? Well, I want to write down what you were told in Math 100. You were told x to the first power means 1 factor of x. You were told that x squared means 2 factors of x. You were told that x cubed meant 3 factors of x. And these are what you were told. Then they said, what would happen if you had x0? Well, there would be no x's to put down. That's what that means. Let me just back up. That doesn't look like a 0. There's no x to put down. Then the question comes is, what's the coefficient? Well, the coefficient in front of all these guys is 1. So this is 1 followed by no x's. So that's been covered. The only one to point out, your teacher's Math 100 also said, what happens if you went backwards? Well, what does that mean? 1, there's still a 1 there, but now the x is in the bottom. So it's 1 factor of x in the bottom. What's x minus 2 equal? 1's still there, but x squared is in the bottom now. All right. So this was covered in Math 100, and it's important you know that. All right. So what's the next thing up? Rules of exponents. And here's the deal. we're hoping that in Math 100, you practice these rules and made sense out of them. And what rules are we talking about? Certainly this one. Let me just go through that with you. This one, and you would need to know these from Math 100. This one, this one. I want to point out though, if you think back to Math 100, they said most of these things were reasonable statements, that you could do these using your fingers. What you couldn't have done with your fingers was dealt with the negative exponents. So write that down. So in Math 100, basically they box 3 rules. I'm going to go to the next page, and I want to tell you what those 3 rules they box that students found horribly difficult to deal with. I'm going to put a box on these rules over here. This rule here, this rule here, and this rule over here. There's 3 rules that they recommended in Math 100 that you tried to make sense out of, but a lot of students couldn't make sense out of. And what do they revolve around? Negative exponents. So I want to point out, if you see a negative exponent, right? If you see it, I'm going to point out what I'm seeing over here. If you see a negative exponent, if you see a negative exponent, what they're asking you to do is immediately rewrite it so it's a positive. So in number 7, what does the x minus n equal? 1 over x to the n. Provided x not equal to 0. What does that 1 over x to the minus n equal? X to the n. Again, provide x not equal to 0. What's the ratio xy to raised power minus n? Well, it's going to be the reciprocal raised to the nth power. Again, provide that y and x are not equal to 0. All right. This one over here, relatively simple. You could have used your fingers to do that. And that was even true when the exponents weren't integer, but they were real numbers. But what did you learn first? Integer exponents. All right. Next up is Euler's number. And I want to point out that Euler, all right, I want to emphasize to you, Euler is spelled E-U-L-E-R, but his name is pronounced like Euler. All right. Swiss mathematician, right? Really famous, has a number reserved for him. And what's the number going to be? It's going to be a limit problem. And where do we see limits? We saw limits in prior sections, particularly with the rational functions. Well, now this is a rational function, 1 plus 1 over x raised to the x power. All right, let me point this out to you. This is really important over here. So what am I seeing over here? I'm seeing a rational function. That's 1 plus 1 over x raised to the power x. This will equal Euler's number. Euler's number is considered one of the most, it's one of the 5 most important numbers in mathematics. And I just want to just briefly talk about that. No need to memorize though. It's this relationship over, whoops, sorry about that. It's this relationship over here. There's 5 numbers there. I'll tell you what those numbers are. 0, you've seen that many times. This had a profound effect on humanity, that the comprehension of 0 is a really important step in our understanding of arithmetic in general. The number 1, super important. It's basis of our number system. All right. Euler's number, super, super important. I see it. What else do I see? The symbol pi, that is a number. And the symbol I, that is a number. So what are the 5 most important numbers? I'll write them down for you. Certainly 1, 0, E, I, and pi. Have you seen all those numbers before? Well, you've certainly seen 1. You've certainly seen 0. You've certainly seen I in Math 100. You've certainly seen pi, even in grade school. E, this is the first time you're seeing it. So someone says, how would you do that? Well, I want to be honest with you. If I were to look at that, I guess I could get an approximate to A. And I want to point out what I mean by that. If you were told that, limit as x goes to infinity, 1 plus 1 over x to the x power was equal E, and you were saying, I wonder what E looks like, what you could do is make a table up. And what would the table look like? X, 1 plus 1 over x to the x power. And then what do? You walk towards the infinity. Now, I'm going to say most people have a tough time with that, but I think probably you would agree that 1,000 is a fairly big number. Are we close to infinity? No, but you're close to a big number. What's the next big number? I would say 10,000. What comes after 10,000? I'd say 100,000. Now, if you play this game forever, the next number would be a million, then 10 million, 100 million. Where's it going to infinity? What you'd have to do, though, is compute this, which is 1 plus 1 over 1,000 raised, I'll use the caret there, to the 1,000 power. And you could do that on a computer. You could do the next one on a computer. No, I wouldn't want to do that by hand. 1 over 10,000 raised to the 10,000. And the next one, what's that going to be? 1 plus 1 over 100,000. And again, a computer can do this quite easily. A quicker way of doing this, I want to point out, if you look on your calculator, you're going to see the symbol E caret. You're going to see that in your calculator. Well, if you do this on a computer and you put E caret, it'll display on the screen. They'll say, what's the exponent? You say 1. What's it going to give you back? It's going to give you back an approximation if you use a decimal. If you don't use a decimal, like if you use this over here, let me just write this down for you. If you don't use a decimal, your calculator will return E. If you use a decimal, that's a caret, by the way, like 1.0, what's your calculator going to do? It's going to approximate this. You should do that in the notes. You should notice I give you the approximate for E. Let me go back. All right. We talked about Euler's number. It's defined as a limit. The symbol of it is E. It's reserved for Euler's number. Let's go to the next page. And I do want to point out and look at the bottom of the page. I know this seems difficult to you. No, we're not asking you to memorize. But I do want to point out at the very bottom of the page, I give you a fairly good approximate value for A. And what is it? 2.7 something. Now someone goes out, how long would this go on? Here's the crazy thing. It goes on forever without a discernible pattern. Now someone says, oh, you stop there. This goes on forever. It's an irrational number. It cannot be written as a ratio in integers. All right, it's an irrational number. All right, let's go back. Let's talk about it. And there's going to be some formulas with that. But I do want to point out, I did mention the word irrational to you. Let me point out what irrational means. Irrational means it cannot be written as a ratio of 2 integers. So it cannot be written as a ratio of 2 integers. By the way, the other number that you know that can't be written as a ratio of 2 integers is the number pi. Pi cannot be written as a ratio of 2 integers. All right, your calculator can approximate it though. We did talk about that. Again, for those students finding their calculator is very difficult to use, come by during office hours and we can walk you through those steps, including you want to see how Sage can get A, right? We can actually help you with that as well, right? We can also show you how Sage can do that limit, all right? So here's some formulas that I'm going to say you need to know when you're doing the homework. You need to know discrete compound. And I would say in general, you should know discrete compound interest anyway. It's something that's common, all right? So I'm gonna read through it. It says the principal. The principal is P, all right? And that's what you're investing at an annual interest rate. So you're investing this. It's invested. P dollars is invested. Typically, where people invest money, I hate to say this, in the bank. And what does the bank do? It returns an interest rate, all right? And the interest rate nowadays are pretty bad, all right? So you give the bank P dollars. The bank says, we're going to give you interest for it. And what they do is they compute interest for it, all right, over time. Now, typically, you know, when does the bank do it? Maybe they do it once a day. Maybe they do it once an hour. Maybe do it once a week. Maybe they do it once a month. Maybe do it each quarter of the year. It depends, all right? So anyway, it's compounded n times per year. And what does that mean? They could do it once per day. That would be 365 times per year, approximately. They could do it once per month. What does that mean? 12 times per year. They could do it once per week. What does that mean? 52 weeks per year. And you get the idea. Could they do it every second? Of course they could, but that's a large number of seconds. Could they do it for every hour? Of course they did, but there's a large number of hours, but they could do it, all right? And they could also do it continuously, which we'll get to later. The amount of money AT, and that is a function of P, by the way, because P is going to, I'm sorry, a function of T, but it involves R and P as well. And P and R are going to be constants, all right? They give me a formula. All right, we will go to examples. For the most part, this is going to require the use of a calculator. Now, whether it's one of those dinosaur calculators you have, that those calculators you hold in your hand, your cell phone, which is great for a calculator, or the internet, or you're using software like Sage or something else, you can do that, and we'll go through that. What's the next one going to be? It's going to be the compound interest problem. All right, so compound interest, and it's going to be continuous. What does that mean? The interest is being computed every moment of time. And that's tough to understand. I know that. But we still have P dollars invested. We still have an annual interest rate of R. And we'll go through examples, by the way, but it's continuously, it's always being computed. There isn't any discrete measure of time for this. It's always going on. All right. And what are you going to do? You're going to generate money. And that's the formula for it. Again, this is going to require the use of a calculator. All right, last but not least, there will be some application problems. The application problems are either going to be growth or decay. These guys over here, let me just point that out to you, are considered growth problems. And why is that? The money increases over time. This is a growth problem. Are there decay problems? Yeah, there's decay. All right. I always say that if you look at humanity, we're in a constant state of decay. All right. We age, we're in decay. All right. Now I'm thinking that, in our universe, the big decay problem would be radioactive decay, that particles have, radioactivity, and over time they reduce in their radioactivity. There's a decay problem. So we're going to see growth. We will see growth of money, but we're also going to see decay. Typical decay is radioactive decay. Now here's another one. It's kind of a sad one, but there's also population growth and decay. All right. Now, what are we experiencing now? I mean, we're, really big growth in human population, but we're seeing decay in some animal populations. All right. Now it happens. So there's going to be growth and decay models. All right. These are actually a lot more complicated. And if you study mathematics more, you're going to notice that what we tell you is not strictly true, except for very simple things like growth of money and radioactive decay. But really, population growths are much more complicated. They're what's known as logistic. All right. So when we get to the examples, I want to point out, we will go through the examples. As we do that, basically some of these things are going to be calculator usage. I would recommend you have a calculator ready to do some of these problems, but I will talk through that for you. Okay, thank you.